Okay, see if we can get this to show up. If I pluck this chain, we can see the pulse traveling down, back, down, back, down, back. Okay. And the tighter I pull the chain, the faster, the more frequently we see it traveling down, coming back, reflecting, traveling back down, and so forth. If I let this chain go pretty slack, it happens a little more slowly. Okay, now this chain consists of paper clips, each paper clip about a gram, and each paper clip, I think, about, what is it? Okay, if I do this, there's 1, 2, 3, 4, 5. Yeah, each paper clip about 4 or 5 centimeters long. Okay, so the paper clips are each about 4.5 centimeters long. It's basically about 4.5 centimeters. So I have paper clip chain. It's about, oh, let's see, about 2.5 meters long. We'll grab paper clips. And they're 4.5 centimeters long. Okay. When I plucked it, pulse traveled 5 meter round trip in maybe half a second. Does that make sense? It seem about right? Now you got the video. If you got the means to time it, you probably have a timer on your phone, download one on your computer, whatever. You could probably come up with a pretty good estimate of the time. Okay. Now, more tension implied. Faster propagation. I think we can see that from the video, because of course, the more tension, the less sag there is in the chain. Now, if we knew the exact amount of sag and did a little bit of fairly complicated calculus, then we could determine something like the average tension in that chain. But we're not going to do that. Okay. What we are going to do is going to say that, okay, impulse momentum theorem implies that C, the speed of propagation, is the square root of tension over the mass per unit length. And I'm not going to define these on the board as mass over unit length. So first place, what's the mass per unit length of this chain? Is Okay. Okay, now we have direct evidence as well, what's the mass per unit length, and we got an immediate answer. Point oh 045. A meter of that does not weigh or have a mass of 0.2 of a kilogram. Okay, it's pretty light. And of course, a meter of it, you can also figure a meter of it would be 22 paper clips, and 22 paper clips would be 22 grams, which is 0.022 kilograms. So we're getting the idea of the mass per unit length. Okay. Another thing about tension is the tension in the chain is greater at the ends than it is in the middle. It's a little bit of stuff we did early in the semester, some of the problems that you would have looked at, established that. The tension in the ends has a vertical component that supports the weight of the chain. If you get the angle at the ends, I said the tension in the ends is equal to the weight of the chain. That's not right. The vertical component of the tension is equal to half the weight of the chain. Okay. And then from the angle here, you know what the vertical component is, you know what the angle of the end is, you can easily calculate the tension in the ends. Okay, tension at the middle is the horizontal component of that tension because the middle isn't moving. Okay, so you can analyze that pretty simple, just simple trig if you get the right picture. Okay, so the point is then that the tension in the ends is greater than the tension at the middle because tension in the middle is just a horizontal component of the tension at the ends. And the difference just depends on the angle of the chain at the ends. The angle is fairly small, so the horizontal component of the tension at the ends. I talk about the angle of the chain at the ends. Okay, assuming it's the same height at both ends. Angle of chain at the ends is fairly small. So even with the greatest seg that we saw on the video, the horizontal component of this tension is probably going to be at least 90% of the horizontal of the total tension. So the point is tension varies. And if this is correct, and it is, and it works out quite well if you do the observations, the tension is slightly variable, maybe a 10% variance in the tension. So you got to kind of keep that in mind. Okay, well, anyhow, there's your mass per unit length. Now, see, propagation velocity. Now, propagation, the thing propagates. The paperclip here doesn't move until the one before it moves. Okay, each paperclip transmits a force to the adjacent paperclip in a way that I love to develop, but in this kind of quick survey, might not get to do it, but we might. And that development leads directly to the wave equation, which says that the second partial derivative of the, well, I haven't defined the terms. Second partial derivative of the displacement from equilibrium is proportional by C, or 1 over C, to the second derivative for with respect to position. We might develop that. It's an important equation. Okay, so C is your propagation velocity. It's the speed with which a disturbance in this paper clip is basically transmitted to the next. Okay? Or the displacement of this paper clip is transmitted to the next. And it's what we perceive as how fast that pulse is moving, which was clearly 5 meters in half a second. So what's our propagation velocity based on this estimate? Well, it's 5 meters divided by a half second, 10 meters per second. Might have been that fast, might not have been. You can look at the video and see. AC is approximately 10 meters per second. Okay. Well, what was the tension? Can you work it out? Okay, we got an estimate. I got it. Okay. The reciprocal of just looking at the numbers, the units work out. Tension is in newtons. This is in kilograms per meter. So you have Newton meters per second squared divided by kilograms per meter is going to give you meters squared per second squared here. And the square root is going to give you units of velocity. Okay, so that's straightforward. You check out your dimensions. It's very, very straightforward for this case. Now, that means if this is in SI units of kilograms per meter, well, then the tension divided by the mass per unit length would just have numerical value of tension over 0.022, which is about 45 times the tension. And the square root of 45 times the tension is about 7 times the square root. Well, sorry, we want the tension, okay? So 45 times the tension should equal the square of the propagation velocity, which means that 45 times the tension ought to be, what, 100 meters squared, meters per second. So the tension ought to be about half a newton. 2 newtons, sorry. That's around what you got. I think you said maybe 2 point something. Okay. Well, we could do it formally, but you can do a mental calculation if you're good at that. And at least somebody here is, because got about the same thing I did. Either we're both crazy or we did it right. A little bit of both, maybe. Okay, so if you want to do it formally, of course, you say T equals C over mu. So T equals C squared mu, which is approximately 100 meters squared per second squared. 5.022 kilogram per meter, which is about 2.2 newtons. And you can check out your units. The meter divides a meter, so you end up with a kilogram meter per second squared, which is a newton. Okay. Your dimensions work out. Okay, well, that's about half a pound. I tell you, my fingers weren't straining. If it had been a pound, boy, they'd have been hurt. But it was a pretty small tension. Okay. Interestingly, what's the weight of that chain? Well, it's 2.5 meters long, 2.5 times 0.022 is 0.04. Well, let's see. The brain just kind of shut off there for a minute. Yes, 0.09 or about 0.1 kilogram, 100 grams. And we can double check that. 4.5 centimeters long, you're gonna have about 50 of them. It's about 50 grams. What am I doing wrong? Okay, well, let's just see. I'm gonna weigh the chain. Just gonna take a second. So I'll just walk off camera and not follow us. There we go. Okay, about 44 grams. Okay. And 44 times 0.022. What am I doing? No, 44 divided. Never mind. Okay. Something's not clicking in my brain today. 2.5 liters times 0.022 would be about, oh, it'd be exactly 55 grams. Okay. So what's wrong? Well, I didn't actually measure the length of the chain. I said it's about 2.5 meters. Okay. Maybe a little more, a little less. Figure out which. All right. Now the picture I want to look at. I guess about what the chain looked like. So the weight. Ballpark. 0.05 kilograms. And that's not too far off. It's 55 grams, but I was holding one of the paper clips and another one was under this thing, so I did bring it down to 53. Okay, so it's about 0.05 kilogram up. Mass. So the weight is approximately 0.5 newtons. So the tension something's going to come out inconsistent here, but just gonna live with it. The vertical component of the tension here well, the force we need here which would be equal and opposite to the tension, is going to have a vertical component and a horizontal component. If the shape is as I've pictured it, it looks pretty close to a 30-degree angle at the end, which means that your vertical component would be about half the tension. I could shortcut that and say the whole tension. Well, with this vertical component of the tension at each end is going to be 0.25 newtons. Because it's the vertical component here and the vertical component here that constitute all the vertical forces other than the vertical force exerted by gravity on the chain, and the vertical force exerted by gravity in the chain is half a Newton. So, okay, so each of these has to be a quarter of a Newton. Assuming that's a 30-degree angle, you have this. That's going to be about 0.21 newtons. And that's wrong. I'm treating that as if it's the whole tension. Horizontal component should be that doesn't match up very well with what we have here. So something could be wrong with the way I've analyzed this. Something could be wrong with my numbers. I could have made a factor of 10 error. But see, the tension should be twice this, about 0.5 newtons. And then the horizontal component should be square root of 3 over 2 times that, and closer to 0.45 newtons. That's not all that close to the 2.2 newtons we got from the equations. So that's worth thinking about. Now, what we really want to focus on is motion of the wave, okay? So I'm gonna go away from this, and I'm doing all this just to make the tension kind of real. Give us some intuitive grasp of how the tension works in that situation. But now we're just going to assume that we have a chain now of length L and it's straight. So we've got mass M, length L, tension T. And instead of U, I'll write M over L. I don't remember which way your textbook writes it. We oscillate one end at frequency F. So how far does the wave travel? For each oscillation? Give me an expression for that. Okay, got the immediate response. We'll say we'll call this the X direction. It's reciprocal of the frequency because the frequency is reciprocal of how long it takes. Okay, if it's oscillating at 5 cycles per second, then it takes a fifth of a second per cycle. Okay, if it takes a quarter of a second per cycle, then the frequency is 4 cycles per second. Okay, so you have that reciprocal relationship, which is pretty natural, but you want to think about it. So we got this immediately. That's something that really good intuition here. 1 over F times C equals 1 over F times the squared tension over mass per unit length. It's not a formula you want to memorize because it's so easy to use this, which is something you probably want to memorize. But you can derive it from the impulse momentum theorem. And you can look that up if you wish, or if we have time, I'll derive it for you. So we have this expression that just combines the meaning of frequency with formula for velocity. That's how far we go in one oscillation. It's delta x per cycle is this. Well, delta x per cycle has a name. First of all, the symbol's lambda, and it's a wavelength. Because what's happening, if you have a harmonic oscillation, a simple harmonic oscillator at the end, what you end up with is then a wave propagating so that the peak to peak distance is lambda or your speed of propagation divided by your frequency. And the simplest relation to remember between wavelength, speed, propagation speed, and frequency is C equals F lambda, which makes sense also. How fast does it propagate? Well, you multiply how many times it oscillates per unit of time with the distance it travels during an oscillation. Okay, because that's all lambda is, distance traveled during an oscillation. I haven't labeled this as wavelength. There's a wavelength. Okay. I'm gonna write down the wave equation for you. Everybody's had differential equations. Okay, let me clarify, and there's something I'm gonna write in here. It's either gonna be C or the reciprocal of C. I never remember which, but dimensional analysis tells you instantly which one it is, okay? So it's either C or reciprocal of C, and this is sometimes written different ways. Sometimes you write it so the reciprocal of C is in front of one of these terms. Sometimes you reverse the terms and write it so C is in front of one of them, whatever's convenient. It's a partial differential equation that isn't that hard to solve. for simple situations and totally impossible for others. As is the case with most partial differential equations. Okay. Why? Let's back up a second so we can talk about the meaning of y before we write this down. Y is, of course, in this direction. And what you have at any point on the wave is you have simple harmonic motion. And it should be halfway evident. Where's my purple chalk? I just have a real strong desire to write this in purple. Okay. I don't know if this thing's gonna work, but let's look here. Okay, let's just take this point here. Now, this is the position of the particle that was originally at this position on the wave. Now, we're assuming a lot of things about the medium. I'm not going to list them all. But we're basically assuming that the particle doesn't have a lot of motion in this direction, that the motion is transverse, which means perpendicular to the original direction of the medium. Okay. So this particle is oscillating up and down. Well, as the oscillation continues, you assume then that this thing is going to continue propagating so that eventually this point will end up here. Okay. And similarly, this valley will end up here. At a different time, this peak will end up here. So that this particle is oscillating between the valley and the peak. And we're assuming that energy is conserved, or that total mechanical energy is conserved. There's no dissipation, so that the amplitude of this oscillation, and I think everybody that had differential equations is familiar with the term amplitude, but in case not, it's just the maximum displacement of the maximum distance of any point on the graph from its equilibrium position. Okay. It's pretty obvious that this particle is oscillating between here and here. So I'm just going to every particle undergoes a transverse oscillation. Frequency F. There's some unstated assumptions behind that. We're trying to give an overview, okay? Because we're doing a fairly quick sketch of waves. And the amplitude is A. So my picture's too small. But the amplitude would be distance from here to here, distance from here to here. Total distance between these dotted lines would be twice the amplitude. All right. Now with that, we're talking about at any point on the graph for any x measured in this direction, the second derivative of the transverse position with respect to x is related to the second derivative of that transverse position with respect to t. 19 needs a 2 on there. Okay. The reason for that's fairly simple. Probably get into that after you've had a chance to look through the introductory problem sets. Simply has to do with the fact that at this position, the particle has a downward component of the force that's proportional to the trying to say it in a way that makes the connection. and I can't without a good picture, I have to do that. The picture looks like this. At this point, the tension is in this direction. So there's a component of the tension in this direction. So that's a downward acceleration, which is second derivative of y proportional to the second derivative of its position here with respect to time. Okay? In other words, second derivative of y with respect to t is the acceleration of this thing, and it's proportional to this component of the tension that's proportional to the second derivative of y with respect to x. And I don't want to flesh out the picture any more than that. Okay, now the question is, and the second derivative of y with respect to x is the curvature. When I say this is the tension, I spoke incorrectly. Let me say it right. Here you got the particle. Here you've got a segment of the wave to the right, and here you've got a segment of the wave to the left. You have a downward concavity so that this segment makes a different angle with horizontal than this segment. This segment has a greater component of the tension, which is downward in this case, than this segment, which is a small upward component. And I should draw it bigger. It's the difference in the slopes of these things, which is your second derivative of y with respect to x, related to the second derivative of y with respect to x. Okay, the derivative gives you the slope here and the slope here. The change in the slope is related to the second derivative, and the change in the slope tells you the net of the tension component to this side plus the tension component to this side. Okay. And that takes a little development, a bigger picture. There's your second derivative of y with respect to x. And this is your acceleration, which is the second derivative of y with respect to t. Now the question is, and the only thing I was going to do is, where do we put c? Well, what are the units here? Units here are going to be like length units per time squared, like meters per second, meters per meter squared, which is reciprocal meter squared. Units here would be meters per second squared. Okay, so we got reciprocal meters on this side, meters per second on this side. If we put one over c squared, then that's going to balance the meters squared we would have here if we multiply by the meter over here, divided by the second squared here. So there's your picture, and just do the dimensional analysis. This side has units of reciprocal meters. This side has units of meters over second squared. Reciprocal c squared has units of second squared over meter, or length squared times squared over length squared. And if you multiply these, you get reciprocal meters, so that's got to be it. And so you kind of work that out. Okay. Now I mentioned the wave equation, because we do talk about it in the introductory problem sets. We kind of developed this picture, and there's some pictures that go with it. People confuse this with the equation of the wave, which I'm going to show you. Okay, well, what we then have is bigger picture. of this wave propagating. And let's say, just say it keeps going, it's propagating to the right. Again, your wavelength. I'll draw it here. It is your peak to peak distance, but that's of course the same as the distance from the node to the point where you're at the equilibrium position. We skip the equilibrium position, go to the next, so that the wave has the same shape here as it does here. There's your lambda. Got frequency F. So what equals what? I'm just going to write it out. Okay. Got some symbols here. There's A, your amplitude. Here's A. Here's A. Look at the mathematics of this description. And Y equals A times cosine kx minus omega t plus some constant phase angle. It's obvious that this is going to give you a wave that looks like this with amplitude A. His cosine varies from -1 to 1. To figure out the relationship between and K, is 2 pi over lambda. This is called the wave number. Go back to the idea of a horizontal shift. In X, this is K times the quantity X minus omega over K times T. So it shifts at speed omega over K. Does that halfway make sense? Maybe not. So let's just review what a shifting transformation does. That's your basic transformation for pre-calculus. And there's a simple reason for it. X has to be H greater in order to give f of X the same value. In other words, if f of X is like a one-to-one function that takes value 12, then when's f of X minus H going to take value 12? When X is H bigger than it was here. That's just a purely mathematical way to understand that the propagation speed is omega over k. Now, there are other ways in the introductory problem sets will develop them because we don't do it this way there. Omega over k, of course, if k is 2 pi over lambda, this is lambda omega over 2 pi. Omega is measured in radians per second. If we divide the number of radians per second by 2 pi, we get like the number of meters per second along the arc and all that kind of stuff. So we get this. Okay. Okay, I had to write this small. And this is not what I planned to do today, but since 2/3 of the class isn't here, I'm kind of improvising something a little different than what I planned. Okay, so anyhow, this lambda omega over 2 pi is just f lambda because what's the frequency? Frequency is number of cycles per second. Omega is number of radians per second. There are 2 pi radians in a cycle. So if you divide number of radians per second by 2 pi, you get the number of cycles per second. Okay. So you want to sort that out. You want to try to understand that as best you can. There are other ways to see it. But we have this. So we can say that what's left there. Yeah. Eat that. Use that. think I forgot to record while I was moving things around. All right, so here's a basic picture. There's your amplitude. Um, you have some frequency F. I'm claiming that the function, that the Y, that the function that gives you the movement of a point on the medium is Y equals A cosine of kx minus omega t. That's a function of two variables, Y plus T, X. Okay, Y is a function of two variables. First place it makes sense is this wave equation is a function of both X and T. Okay, the position of a point on the graph depends where you are and what the time is. Transverse position. Can you quickly verify that this function satisfies this? Probably do in your head if you think about it. But if you need to do it in paper, that's okay. Okay, think about it now. Maybe a little hard to do in your head, probably not giving you enough time to do it on paper. Take the second derivative of this thing with respect to x. Each time you're going to get a k out of the chain rule, right? And you're going to get back to the same function you started with, except you're going to have a negative sign. So you're going to get a negative k squared times this, okay? Well, that gives you a negative k squared times your y function here, right? Now do it with respect to t. You're going to get a negative omega squared times this. So you're going to get a negative k squared times your y function here, a negative omega squared times your y function here, okay? If you then take the omega squared and divide by the k squared, you got omega squared over k squared here. And multiply both sides by c squared, you got c squared over here. So this gives you c squared equals omega squared over k squared. If you don't see that, okay, write it out. Just write out the derivatives and you put them in here and see that everything cancels out except c squared equals omega squared over k squared. But of course, c is or is it's lambda omega over 2 pi, but lambda is 2 pi over k, and it all works out. Okay. And we don't need that because we figured that the speed is omega over k. So speed squared should be omega squared over k squared. And that's the simplest way to see it. It just comes right out. When we graph the thing, the other thing I'm going to mention is it doesn't make a bit of difference that we have a cosine here. If this is any function f of kx minus omega t, any function f of kx minus omega t, same thing's going to happen. So it doesn't have to be a sine wave or cosine wave. However, that's what we're going to kind of confine our attention to since we're doing a fairly brief survey. Okay, so So here's your delta X. It's gotta be equal to C delta T, and that's gotta be equal to omega over K delta T. Because of what we said here, the horizontal shift and so forth. Important picture, you want to sort that out. See how this works together. If you do, then you bypass a whole lot of reading an explanation. If not, you can read and work out some problems. Last thing, I drew this as a string between 2 points. I haven't mentioned what happens when the wave gets here. When the wave starts out like so, you got this pulse. Then you have an opposite pulse, but this pulse keeps going. And then eventually, you get here, and the disturbance meets this end. When it does, again by the impulse momentum theorem, it doesn't continue going, it reflects. So now you get something like this. And I didn't draw that quite right because it looks like you get a flat line. And maybe for an instant you do, but it's not going to last. Okay. If the wavelength matches the distance between these points, then the wave will get to this end. Well, the wave will fit at some integer number of half wavelengths between here, so that the reflected pulses will reinforce the pulses that travel down. Okay, and that's called a standing wave. If it just keeps going, it's a traveling wave. So in this case, it's a traveling wave until it first gets here, then it starts messing and superposing with its reflections, and things get all complicated. So that's all I'm going to say about that, because we're out of time. I will develop these ideas, but I'm going to assign everybody to read as thoroughly as they can through the introductory problem sets, so you get a lot of these details. And then we can better understand the mathematical description and the things we do with the mathematics. Okay. That's all right. I was a little incoherent. I, had to switch plans because we didn't have enough people to do what we were going to do. But hopefully that'll give you a good introduction once you think through it.